Changing state. Equilibrium is a dynamic condition in which two opposing changes occur at equal rates in a closed system. In a closed system, matter cannot enter or leave, but energy can. In an open system, both matter and energy can escape or enter. For example, sunlight, heat from a burner, or cooling by ice can cause energy to enter or leave a system. So these are all of the possible changes of state. A lot of them are, well, hopefully most of them are pretty obvious. And so we've got solid to liquid is melting, an example is ice melting to water. Solid to gas sublimation, liquid to solid is freezing, liquid to gas vaporization, gas to liquid condensation, and gas to solid is called deposition. Consider the evaporation of water in a closed container. Assume that the contents of the container maintain the same temperature as the surroundings around 25 degrees Celsius. The water and the container together are the system. Initially, there is a single phase inside the system, the liquid phase. A phase is any part of a system that has uniform composition and properties. It's another word for state. If the energy of a water molecule at the upper surface of that liquid is high enough, the molecule can overcome the attraction of neighboring molecules, leaving the liquid phase and evaporate. Water molecules that have entered the vapor phase behave like gas molecules. So what I mean when I say that is basically when you start off, let's say you put a liquid in a flask and you put a stopper in the flask. So this makes it a closed system. So matter cannot leave. The only phase that is present in the beginning is the liquid phase. But at the surface of this liquid, you'll have different liquid molecules that have different kinetic energies, and some of those kinetic energies will be enough to overcome the attractive forces and have it escape as a gas. For part C, this is when equilibrium occurs, because in part B, when you first have liquid molecules that escape and enter the gas phase, what's going to happen, because remember it's that fight between kinetic energy and intermolecular forces. So the reason why the liquid molecule was able to evaporate as a gas is because it had enough kinetic energy to overcome the attractive forces. So as it's bouncing around in here, it's going to lose some kinetic energy and it will start to what's called condense. So it might hit the top of the cork here, it might hit the sides of the glass, but as it loses kinetic energy, then that means if kinetic energy is getting lower, then that means that the attractive forces start to win and it can condense back into the liquid state. Equilibrium is reached when the rate of evaporation equals the rate of condensation. Those are two opposite processes. Evaporation, liquid to gas, condensation, gas to liquid. That's when you reach equilibrium. So here you can see condensation forming on the outside of what looks like a Coke can. So some of the vapor molecules are going to move down toward the liquid surface and condense. So they will re-enter the liquid phase. So condensation, again, is the process by which a gas changes to a liquid. If the temperature and surface area of the liquid remain constant, the rate at which the molecules enter the vapor phase remains constant. The rate at which the water molecules pass from vapor to liquid phase depends on the concentration of molecules in the vapor phase. The concentration of vapor molecules and therefore the rate of condensation is initially 0. Like I said in that very first, diagram here, A is the initial phase. There is 0 condensation because there is 0 vapor molecules. as the number of vapor molecules increases, therefore the rate of condensation increases until they are both equal. Okay, so the vapor molecules in equilibrium with a liquid in a closed system exert a pressure that is proportional to the vapor concentration. That is called equilibrium vapor pressure of the liquid. So in the animation you see on the bottom right-hand corner, you can see some molecules that are condensing and some molecules evaporating. So that little mass of red circles on the bottom, that is the liquid. The gas above the liquid exerts a pressure that is proportional to how much gas there is, which makes sense because what creates pressure are gas molecules. If you have more gas molecules, you have more pressure. So equilibrium vapor pressure of a liquid is the pressure exerted by a vapor in equilibrium with its corresponding liquid at a given temperature. It's going to be specific for the temperature because what happens if you increase the temperature of a closed system? When you increase temperature, you're going to increase kinetic energy, which means you're going to have more molecules entering the vapor phase, which means condensation increases, which means evaporation will increase as well. You'll establish a new equilibrium with a higher concentration of vapor molecules. And so at a higher temperature, you will have a higher equilibrium vapor pressure. Here is a graph of 3 different liquids and their vapor pressure. Like I said, vapor pressure increases as you increase temperature. So you can see why it increases as temperature increases. We have diethyl ether, we have ethanol, and we have water. Now, why do you think water has such a significantly higher vapor pressure than the other 2 liquids? It's the same thing that I told you last year when I ask you any time about water and why water is different in any way. The answer is polarity and hydrogen bonds. So water is a very highly polar molecule. It has a high degree of hydrogen bonding, which means its vapor pressure is going to be significantly higher, especially at higher temperatures. So the curve shows that at any given temperature, the vapor in equilibrium with the liquid exerts a specific vapor pressure. And again, if temperature increases, vapor pressure also increases. The increase in equilibrium vapor pressure with increasing temperature can be explained using the KM theory for liquids and gases, which is the whole point of this unit. Increasing temperature increases kinetic energy. That in turn increases the number of molecules that have enough energy to escape from the liquid phase into the vapor phase, as I said before. The resulting increased evaporation rate increases the concentration of vapor molecules, which will then increase the equilibrium vapor pressure. So when you start at, say, 25 degrees and you establish equilibrium at 25 degrees and then you increase to 50 degrees, you disrupt or disturb that equilibrium. If you wait a set amount of time, you can reestablish a new equilibrium at a higher vapor pressure. So when going back to when we have an increase in temperature, increase in kinetic energy, which means an increase in vapor molecules, that means that there's an increase in condensation because condensation is going to be proportional to how many vapor molecules there are. And again, equilibrium will be reestablished, but at a higher equilibrium vapor pressure. Now, based on the rate of evaporation, we can classify liquids as volatile or non-volatile. This is due to the attractive forces holding the liquid particles together. The stronger the attractive forces are, the smaller the percentage of liquid particles that can evaporate at a given temperature. The low percentage of evaporation results in a low equilibrium vapor pressure. I should go back and redefine what I meant for this this graph. I don't know how to take that out. Anyway, I don't have an eraser for the Keynote app, but anyway, so okay, it doesn't matter. What this graph really shows you, not necessarily that water has a higher vapor pressure, because you can see if you compare the two, let's say if 400 for diethyl ether doesn't require a very high temperature, it's like say 10, and for a pressure of 400 torr for ethanol is around 60, and for water is about 80. So the difference in temperature is what tells you about the polarity, because you think about what polarity is in hydrogen bonding. It's keeping the liquid particles together as a liquid. So it takes a higher temperature to create the same amount of pressure that a different liquid can do at a lower temperature. This is the difference between volatile and non-volatile liquids. A volatile liquid is one that evaporates very easily. So at lower temperatures, you will have evaporation occurring, which means you have a higher equilibrium vapor pressure. For water, because of the hydrogen bonding, it's going to require a higher temperature to create the same amount of pressure that a volatile liquid will create at a lower temperature. This makes water a non-volatile liquid. A really easy way to distinguish between the two, is a volatile liquid evaporates quickly because it has weak attractive forces between particles. Ether, which that left-hand graph was a diethyl ether, is a very typical volatile liquid. So is alcohol, by the way. And that's why alcohol makes your skin feel cold, because it evaporates very quickly and takes all the heat with it. A non-volatile liquid evaporates slowly because they have relatively strong attractive forces between particles. And water is a great example of a non-volatile liquid. So you just think about if it evaporates quickly or not, whether it's volatile or non-volatile. Hey, boy. Okay. Okay, boiling. Boiling is the conversion of a liquid to a vapor with heat. The big difference between boiling and evaporation is whether there's heat or no heat. Boiling occurs when equilibrium vapor pressure is equal to atmospheric pressure. At 1 atm, which is standard pressure, boiling occurs at 100 degrees Celsius. 100 degrees Celsius is when the water molecules have enough kinetic energy to overcome the attractive forces, and the water vapor is at 1 atm. If the temperature of the liquid is increased, the vapor pressure is also increased, like we said before. Finally, you reach boiling point. Boiling point is when is the temperature where the vapor pressure equals atmospheric pressure. This has real life applications. The lower the atmospheric pressure is, the lower the boiling point is. So at high elevations, where atmospheric pressures are lower than sea level, a cooking liquid boils at a lower temperature, so it takes food longer to cook because you don't have the high temperatures. You can't hear him, so I'm just gonna like scan through the video and tell you what's happening. He is in, I believe, Kathmandu. Basically, he's in the city where Mount Everest is, and he's going to show you the temperature where water boils first. at, I don't know what his elevation is here. It's going to be higher than sea level for sure, but he's got his little camping gear, blah, blah, blah. 97, you see that? 97 degrees, and the water is boiling. So still not quite, here we go. Yeah, Kathmandu, 1,300 meters above sea level. So that's why it's boiling at 97 degrees and not 100 degrees. Okay, so 97 degrees at 1.3 kilometers above sea level. So now he's higher up, and you can see 73, 74, 74, 75. Oh, here we go. That was just warming up. 91, so you can see the bubbles on the top there. 91 degrees we're boiling at. And this is at 3.5 kilometers or 3,500 meters above sea level ASL. So we've already decreased by 6 degrees, and that's a difference of 2.2 kilometers. And then I think we're going to do one more. Here we go. This is what they call base camp. Is 82 the final one? 91. Okay, base camp. Yeah, 82. Look at that. 82 degrees at 5,300 meters above sea level. So imagine how much more slowly your food cooks if the water only gets to 82 degrees before it starts to boil. Huge difference. And then he's going to go explain why that is. Anything else? No. I'll say, so when vapor pressure equals atmospheric pressure, boom, the water boils. As you go up a mountain, the atmosphere becomes thinner, therefore atmospheric pressure decreases, therefore boiling occurs at lower temperatures. At the boiling point, all of the heat that is absorbed goes to evaporate the liquid, and the temperature remains constant as long as the pressure does not change. If the pressure above the liquid being heated is increased, the temperature of the liquid will rise until the vapor pressure equals the new pressure and the liquid boils once again. This is the idea behind a pressure cooker, and I'm hoping you can see that picture behind the video. I don't know how to get the video in a different position. I move it around. It's still in the upper right-hand corner. Okay, so a pressure cooker is sealed airtight so that the steam pressure builds up over the surface of the boiling water inside. That increase in pressure increases the boiling temperature, resulting in shorter cooking times. So it's the opposite of what happens as you go up in elevation, that the temperature becomes lower when the water boils. Here, you can create higher than 100 degree temperature without the water boiling because it's sealed. So as it evaporates, it creates a higher pressure, and a higher pressure means higher vapor pressure, and the atmospheric pressure, of course, is inside the pot, which is high. So you can heat water up to a high degree without it boiling, and that decreases cooking time. Okay, and then we also have another real life example of why this matters, and that's called a vacuum evaporator. I'm sure some of you really like eating things with condensed milk. This is how that is created. A vacuum evaporator causes boiling at lower than normal temperatures. They are used to remove water from milk and sugar solutions. That's what creates condensed milk. So inside the vacuum evaporator, there is a reduced pressure. That means that the water boils away at a temperature low enough to avoid scorching or burning the milk or sugar. So both evaporated milk and sweetened condensed milk are made this way. You can heat milk up to make the water part of the milk evaporate, but at a certain temperature, the sugar, the lactose that's in the milk is going to burn. So if you reduce atmospheric pressure, it makes the water boil off at lower temperatures, which means you can condense the milk and make it sweet. As you know from experience, heat must be added continuously in order to keep a liquid boiling. So if you take a boiling pot of water off the stove, it immediately stops boiling. Suppose you were to carefully measure the temperature of a boiling liquid and its vapor. You might be surprised to find out that they are at the same constant temperature. The same thing goes for an equilibrium system between freezing and melting. If you have a glass of ice water that you can keep at 0 degrees, you will forever have a glass of ice water because you will have water freezing and melting at the same rate at equilibrium. The temperature or average kinetic energy of the particles at the boiling point remains constant despite the continuous addition of heat. So where does the added heat energy go? It is used to overcome the attractive forces between molecules of the liquid during the liquid to gas change. And the energy is then stored in the vapor as potential energy. Okay, a couple more things before we finish. The molar heat of vaporization is the amount of heat energy needed to vaporize 1 mole of liquid at its boiling point. It's an indication of the strength of the attractive forces in the liquid. The magnitude of the molar heat of vaporization is a measure of the attractive. Okay, I just said that. The stronger the attraction is, the higher the molar heat of vaporization is going to be. And each liquid has a characteristic molar heat of vaporization. And of course, water has unusually high because of its extensive hydrogen bonding. Okay, freezing. Freezing is changing from a liquid to a solid state. It involves a loss of heat energy, and we can represent it with the word equation: liquid yields solid plus heat energy. That indicates that energy is being lost. For crystalline structures, which I talked about in the Zoom meeting, they have a constant definitive freezing point. And so the freezing point is the temperature at which the solid and liquid are in equilibrium at 1 atm of pressure. The particles of the liquid and solid will have the same average kinetic energy. The loss of energy is the loss of potential energy that was in the liquid. At the same time the energy decreases, the particle order increases because the solid state is much more ordered. So what that means is as the liquid particles lose energy, the attractive forces take over and start to pull the molecules from a random arrangement into an ordered arrangement. Melting also occurs at a constant temperature, and it will occur at the same temperature that freezing occurs because they are opposite processes. As a solid melts, it continuously absorbs heat. So we have the opposite reaction that we saw before. A solid plus heat energy yields a liquid. Okay. Blah, blah. Okay, so an important thing to remember is that the temperature of the system is going to remain constant as long as there is any ice present. The temperature of the system will only increase once all of the ice is melted, because remember, when you're changing state, all of the added energy is going into changing the state, not changing the temperature of the system. The molar heat of fusion is the amount of heat energy required to melt 1 mole of solid. Again, it's an indication of the attractive forces between particles. And finally, sublimation and deposition. This occurs at sufficiently low temperatures and pressures where a liquid cannot exist. In the next video, when I talk about phase diagrams, it'll be more clear what I mean by this. But there are certain temperatures and pressures at which a liquid cannot exist. So the only equilibrium that is available is between a gas and a solid. So that is sublimation, which is changing from a solid to a gas, and deposition, which is changing from a gas directly into a solid. Again, this occurs at temperatures and pressures at which a liquid cannot exist.